In this video, you'll learn about units of decibels and how it's used to characterize the gain of amplifiers. So far, we've expressed voltage gain as the ratio of an output voltage to an input voltage. Therefore, it has units of volts per volt, or actually dimensionless. Whenever we have a dimensionless quantity representing the ratio of two values, it can be useful to represent it on a logarithmic scale. That way, multiplication of the underlying quantities can instead be replaced by addition of their logarithms. Decibels are a way to express gains as a ratio on a logarithmic scale. Specifically, for a voltage gain, we take the log base 10 of the voltage gain in volts per volt multiplied by 20. The result is still dimensionless, but we use the units dB to remind us that it's on this logarithmic scale. For example, if we have a voltage gain of 2 volts per volt, we can express that in dB as 20 times log base 10 of 2. Notice we use the absolute value of the voltage gain because the logarithm of a negative number, strictly speaking, is not defined. If you punch this into a calculator, you'll see that it's very close to a value of 6 dB. This is a useful fact to keep in mind. Whenever you've got a gain of 2 volts per volt, that's equal to 6 dB. Similarly, it's also useful to remember that a voltage gain of 10 volts per volt is equal to precisely 20 dB. Finally, it can be handy to keep in mind that any power of 10 can be easily converted into dB. For example, a voltage gain of 10 to the 4 is simply 20 times log base 10 of 10 to the 4, which is 20 times 4, or 80 dB. Another handy fact to keep in mind is that if you take the square root of a voltage gain, that's like cutting the number of dB gain in half. So for example, if we have an amplifier with a voltage gain of root 2 volts per volt, well, we know that an amplifier with a gain of 2 has 6 dB of gain, and so an amplifier with a voltage gain of root 2 has 3 dB gain. Finally, recognize that if you have the voltage gain in dB, you can always convert it back into the original volts per volt by dividing by 20 and raising it all to the power of 10. That'll give you the magnitude of the voltage gain in units of volts per volt. dB can also be used to express current gains, that is the ratio of an output to an input current, which would normally have gains of amps per amp, but still that's a dimensionless quantity, so we can express it on a logarithmic scale by taking 20 log base 10 of the gain in amps per amp. We mentioned before that expressing things on a logarithmic scale allows us to replace multiplication with addition. Why is this convenient in the case of the gain of amplifiers? Well, amplifiers are often connected in series. For example, let's say you have two amplifiers in series, each with a gain of 2 volts per volt. Well, we know that the total combination of these two amplifiers in series has a gain of 2 times 2 volts per volt, or 4 volts per volt. Alternatively, we can say that the first amplifier is a gain of 6 dB, and that's followed by another amplifier with a gain of 6 dB. So the total combination has a gain of 6 plus 6 dB, or 12 dB. You can confirm this by checking 20 log base 10 of 4 for yourself and see that it works out. Keeping this fact in mind can help you easily convert between dB and volts per volt. For example, if I tell you that an amplifier has a gain of 26 dB, you can recognize that that's the same as a gain of 20 dB in series with a gain of 6 dB. And we know that 20 dB is 10 volts per volt, 6 dB is 2 volts per volt. So 26 dB is actually equivalent to 20 volts per volt. I didn't have to take any logarithms to do that. I just had to remember that 20 dB is 10 volts per volt and 6 dB is 2 volts per volt. One final example of the utility of this kind of logarithmic arithmetic is, say you've got an amplifier with a gain of 42 dB or some other odd number like that, and your boss asks you to double the gain. Of a 42 dB amplifier. Assuming he means double the gain in volts per volt, that's the same as just adding 6 dB to 42, or getting a total gain of 48 dB. Again, no need for logarithms or exponents. So just to review a couple of quick facts, you got a gain, whether it's in volts per volt or amps per amp. It's dimensionless and can be expressed in dB. When you've got a gain of 10, that becomes 20 dB. Gain of 2, 6 dB. It's a voltage or current gain. And a gain of root 2 is 3 dB. Now, in principle, you can also have a gain of just 1. A gain of 1 amps per amp is 0 dB because log of 1 is 0. It may also be useful to keep in mind that you can have a gain less than 1 in the case of an attenuating circuit. In such cases, the gain can still be represented in dB, but then you get a negative value. So for example, a value of a half a volts per volt expressed in dB looks like 20 log base 10 of 2 to the power minus 1, which is negative 20 times log of 2, or negative 6 dB. So a half is negative 6 dB, and similarly a tenth is negative 20 dB, and a gain of 1 over root 2 is negative 3 dB. These can be useful facts to keep in mind as well. We may also be interested in the power gain of an amplifier. That is the ratio of the power delivered to the load to the power delivered from the source. The power delivered to the load is the product of the output voltage VO and IO. The power delivered from the source, or the input power PI, here's the load power PL. The input power PI is the product of the input voltage VI and input current II. So again, we take the ratio of these two quantities. We've got units of watts per watt, which are again dimensionless. So it may again be useful to express that in units of dB on a log scale. But an important thing to note is that when we're expressing a power gain in decibels, we take 10 times log of the power gain in watts per watt, not 20 times log of the gain. So why do we do this? Well, there's a good reason we use 10 times log base 10 of the power gain instead of 20 times log base 10. And you can see it by considering this situation here, where an amplifier has an input resistance, Ri, and is driving a load, RL. So we know the input power delivered here is Vi squared over Ri. And we know that the load delivered the power delivered to the load is VO squared over RL. Therefore, the power gain is the ratio PL over PI. And substituting in, we see that it's VO squared over VI squared times the ratio of RI over RL. If we express this in dB, we take 10 times log base 10 of AP, which is 10 times log of VO over VI squared plus 10 times log of RI over RL. And then this term here, we can rewrite in a form that looks just like the voltage gain, VO over VI, in other words, AV, log of that times 20. So, and then we've got this extra term, it depends on the ratio of the input and output, the input resistance and load resistance here. But this first term here is nothing more than the voltage gain of the amplifier expressed in dB. Therefore, if the voltage gain increases by a certain number of dB, the power gain of that amplifier increases by the same number of dB, assuming the input resistance and load resistance hasn't changed. It may be easier to understand this by way of a simple example. Imagine that the voltage gain of this amplifier doubles. Again, assuming Ri and RL don't change, the power gain, which we've shown is equal to the voltage gain squared times this ratio Ri over RL, quadruples. However, because in the case of a voltage gain, when we express it in dB, we take 20 times log base 10 of AV, whereas with a power gain, we take 10 times log base 10 of AP. Because of that, both will increase by 6 dB. So a 6 dB increase in gain is a 6 dB increase in gain, whether you're talking about voltage gain or power gain. And that can be kind of nice in avoiding confusion, actually.